Hi there, welcome to the Retro Desk. I'm Matt Heffernan. This is the fourth episode in a series that seeks to demystify programming and assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you know when the next episode comes out, and start this playlist from the beginning. Also, this is the second edition of this series, updated to work with the actual hardware. So far in this series, we have introduced the basic concepts of assembly programming and learned how to access memory in different ways through addressing modes and how to implement flow control using branching, jumping, and subroutines. Now that we know how to structure a program, let's start doing what computers were invented for: math. The 6502 family has only rudimentary capabilities for math, but the instruction set is complete enough to do any kind of arithmetic you need to do. You just may need to write a lot of code compared to more modern, comprehensive instruction sets like x86. But don't worry, like our friend Barbie says, math's not that hard, don't be a crybaby. We're going to break it down, bit by bit. All arithmetic done by the 6502 is at the 8-bit level. That is 1 byte at a time and uses 2's complement binary, which is just a fancy way of saying that positive and negative numbers work the same. So the processor doesn't need to be aware of whether a value is interpreted by the program as signed or not. For the purposes of this lesson, we will be assuming that all values are unsigned. We will cover more advanced arithmetic processing in a later episode, so today we are going to stick to the basics. In C, like most high-level languages, arithmetic is done using syntax that is very similar to standard mathematical notation for expressions, and having the assignment target on the left. Stack-based languages like Forth and RPL do it differently, but pretty much all mainstream languages have followed the precedent set by Fortran back in the 1950s. In assembly language, operations can't use this kind of notation. We need to do things one instruction at a time. So for arithmetic, we have only a handful of instructions, including ADC and SBC for addition and subtraction respectively, and 4 instructions used for bit shifting and rotation. In the C code, we see a basic arithmetic operation, where we take the sum of foo and bar and subtract baz from it, then assign that result to the val variable. To do this in assembly, we have to break it down step by step, starting with loading the value of foo into the accumulator. Then we clear the carry bit before adding the value of bar to it and storing the result back in A. Then we set the carry bit before subtracting the value of baz from the previous result, and finally taking the final result and storing it to val. Of course, this is an extremely simple example, but for 8-bit addition and subtraction, that's all you really need to do. Let's take a closer look at the ADC, or add with carry instruction. We've seen it used before in previous lessons, but now we're going to look at exactly what it does. Of course, it does an addition between the value in the accumulator and a value from memory. It also adds in the current state of the carry bit, which means that 1 plus 1 can indeed be 3 if you forgot to clear C first. So the result of adding these 3 values together is the sum, but there is a chance that it won't fit in 8 bits. The lower 8 bits will be stored in A, which would be the same as the sum mod 256. As the sum can range between 0 and 511, the processor uses a set carry bit as the 9th bit for sums that are 256 and larger. If the carry bit is clear after the addition, then we know the sum fits entirely in the accumulator and is therefore 255 or smaller. That carry bit can then be carried into the next operation, enabling 16-bit or wider addition. In the previous episode, we looked at some of the other side effects as well, including when the N, V, and Z bits are set. Here I have some formulas that help formalize what they mean, but in short, N indicates that the highest bit of A has been set. V indicates a different sign of the sum compared to the sign of the operands when they match, and Z indicates the value in A is 0. ADC has a relatively large number of addressing modes, allowing you to add in an immediate value from the instruction or 8 different ways to fetch that value from somewhere else in memory. A new mode available for ADC in the 65C02 is the zero page and direct mode, which was not available on older processors in the 6502 family, like those found in the Commodore 64 or Nintendo Entertainment System. Now with SBC, we have some similar behavior to ADC, except that the handling of the carry bit is inverted. The instruction will subtract the memory value from the value in A. Then if C is clear, it will further subtract 1. This is why we initialize subtraction by setting the carry bit rather than clearing it like we do for addition. This is because C is used effectively as an inverted borrow bit for when the subtraction results in a negative result, requiring a borrow from the next operation to interpret it as positive. Just like the carry bit behavior with ADC, this allows you to have a borrow chain that lets you subtract numbers that are 16 bits or wider. The N, V, and Z bits behave exactly the same as with ADC, and SBC is the only other instruction that can change the V bit as a side effect. Otherwise, you have to store a value to it directly with PLP or CLV. SBC also uses all the same addressing modes as ADC, including the added ability to use the zero-page indirect mode with a 65C02. Let's take another look at the case study we saw earlier, but this time try to implement it as a 16-bit calculation. In C, the syntax of the expression doesn't change based on type. It looks the same whether the result is an 8-bit char, a 16-bit int, or a 32-bit long, or even a floating point value. But every byte of each operand needs to be accounted for in assembly code. So for 16-bit arithmetic, we need to do ADC or SBC instructions for both the low byte and the high byte of the result. As the 6502 is little endian, it makes sense to have your wider integer values start with their lowest byte, with higher bytes coming after. So like before, we load A with the value at foo, but this time we know that is just the low byte, so we'll have to come back for the high byte. For now, we clear C and add in the low byte at bar. Even though we aren't done yet, we need to store this intermediate value, so we go ahead and store that at val temporarily. Then we need to finish the addition by moving on to the high byte of foo and bar by adding 1 to each address at assemble time, adding those while maintaining the state of the carry bit from the last addition. This makes sure the carry happens correctly, just as we would by doing addition by hand with decimal numbers back in elementary school. Now with the high byte of the intermediate result set, we store that to the high byte of val again by letting the assembler calculate that address by putting a +1 in the operand. Now to do the subtraction, we have to retrieve the low byte of our intermediate result. Then make sure the carry bit is set and subtract the low byte of baz from it. Now we have the lower byte of the final result, so we store that back to val. Then we go ahead and do a subtraction of the higher bytes, maintaining the carry state of the previous subtraction so that a borrow can be done if necessary. Then we store the high byte of the final result back to val +1, and we're done. As you can see, making integer values wider results in a lot more assembly code and can slow down the program, so you want to minimize the need to go beyond 8-bit calculations. But if you do need to use bigger numbers, it is not too bad, and can even be done iteratively if you need to get even wider than 16 bits. We've seen how incrementing and decrementing work in earlier videos, but for context, consider how different they are from adding or subtracting 1. First, memory values can be incremented or decremented directly without having to modify any registers when using any of the legacy modes of the inc and dec instructions. The 65C02 actually introduced the implied accumulator mode to inc and dec so that only A is incremented or decremented without having to bring in any memory values or using one of the index registers. Meanwhile, the instructions for index registers are only implied and can never be used with any memory values, just as you can't do any other kind of arithmetic directly with them. To change x or y to a new value, you can either do a bunch of increments or decrements, or do an addition of subtraction by transferring the value to A and doing the arithmetic there before transferring the new value back. In all cases, these instructions do not consider or change the states of the overflow or carry bits, like the ADC and SBC do. You can also see here that the set of addressing modes for inc and dec is smaller than ADC and SBC, notably the lack of indexing with Y or any indirect modes. So we've seen how integer addition and subtraction work, but what about the rest of arithmetic? Well, there are no instructions specifically for multiplication or division, but that doesn't mean it's impossible. What you do have at your disposal are instructions for shifting the bits in the accumulator or at a memory location, and combining that with addition and subtraction can do any kind of arithmetic. Multiplication is fairly straightforward. You just shift a bit to the left to multiply by 2. You can do this repeatedly to multiply by higher powers of 2, and then keep adding the factor to get up to the number you want to multiply to. So multiplying a value by 7 means first shifting the original value 2 bits to the left, then adding that original value to the shifted value 3 more times. You can take many different strategies based on the bit width of the numbers you are dealing with. Division is a bit trickier, as it requires shifting to the right to divide by powers of 2, and then strategies like tentatively subtracting the factor to see if it's getting you closer to where you need to be. Going through a division algorithm is beyond the scope of this lesson, so we'll tackle that in a later episode on advanced math operations. So your best bet for most programs is to avoid having to do multiply or divide anything by something other than a power of 2. This can be accomplished more often than you may think, usually at the cost of efficient data storage. You can pad out data so that array elements are sized by a power of 2, which can make access much faster, but fill up memory with empty space. But that empty space could be overtaken by having a larger code footprint to do more complicated math, which will be slower at any rate. So there are a lot of things to consider when you are structuring your program. Bit shifting is used commonly in languages like C, where you are likely to be doing some kind of system programming close to the hardware. But in assembly language, it is a necessary part of doing anything like multiplication and division. The 6502 family has 4 instructions for doing this, including 2 called rotate that are really just shifting with the carry bit acting as a 9th bit of the value. Shifting left is the same as multiplying by 2, which is exactly what the ASL instruction does, an arithmetic shift left. It puts the highest byte of the target value into the carry bit and then shifts the remaining bits to the left, finally replacing the lowest bit with 0. So while it does affect the carry bit, it does not care what the status of C is going in. The ROL, or rotate left instruction, does the same thing as ASL, but it puts the original state of the C bit into the lowest bit instead of 0. This lets you shift a multi-byte value by chaining ROL instructions on successive memory addresses. Starting with ASL will guarantee that the shift across all the bytes will result in a multiplication by 2. Shifting right is the same as dividing by 2, which is pretty much what the LSR instruction does, logical shift right. Like ASL, it shifts a 0 in, this time into the highest bit, then shifts everything else to the right with the lowest bit going into C. For positive even numbers, this will definitely be a division by 2. For negative numbers, you would probably want to use ROR, or rotate right instead, with the carry bit set going in so that the highest bit stays set. Like with ASL and ROL, LSR and ROR can be chained to shift multi-byte values right and divide large numbers by 2. Going through these chains multiple times can multiply or divide by any power of 2. All 4 shift and rotate instructions have the same set of addressing modes available. They can all operate on just A using the implied accumulator mode. If there is an operand, then the operation is happening directly to a location in memory, with the accumulator left untouched. As you can see, no indirect modes nor anything indexed by Y are supported. Shifting provides a nice segue into doing bitwise logic operations. Like in C, where single ampersands and pipes can be used for bitwise ands and ors, respectively, the same operations are available as assembly instructions. A bitwise AND will let you select specific bits to clear, a bitwise OR will let you select specific bits to set, and a bitwise exclusive OR will let you select specific bits to flip from 0 to 1 or vice versa. In the previous episode, we saw how we were able to convert binary numbers to Petsky characters by setting a couple of bits with the ORA instruction. Here we see how an expression with bitwise operators in C can translate directly to a sequence of bitwise assembly instructions. First, we load the value at foo into A, and then AND it with the value at bar. This means that only the bits that are set in both values will remain set in A. Then we OR the new value in A with the value at baz, which means that all the bits set in baz will now also be set in A, along with any bits that were already set. Next, we do an exclusive OR with boom, which will flip in A any of the bit positions that are set in boom. Finally, we store the result into val and the assignment is done. This may not be a useful sequence of operations in any scenario, but it does show how directly a bitwise operation in a language like C can be translated to assembly. Looking more closely, we can see what each of the 3 bitwise logic instructions do. Starting with AND, or AND with accumulator to be precise, the value in A will be ANDed with a value from memory, effectively masking out a set of bits we care about, or simply clearing bits as needed. OR A, which is OR with accumulator, will do a bitwise OR of the value in A with a value from memory, ensuring that certain bits will be set in A afterward and no others are changed. Finally, EOR is not a depressed donkey, but exclusive OR with accumulator. The value in A will have certain bits flipped as specified by which bits are set in a memory value. All 3 bitwise logic instructions have all the same addressing modes as are available to ADC and SBC, including zero-page indirect, which was added for the 65C02. Now we can see just how important arithmetic and logic are to this processor. With 8-bit opcodes, only 256 unique opcodes are possible, and here are 79 opcodes used for all the addressing modes of the 15 instructions we introduced in this lesson. Armed with this knowledge, we are going to see how arithmetic and logic can be used together in our example program. The example program for this lesson will perform a simple 16-bit addition and print the result in hex. Yes, it seems fairly trivial, but we are going to use a lot of the knowledge we've gained so far to create some code that will actually be useful. Once again, we see the boilerplate at the top of the code to get it to start at hex 80D. Then a constant for the address of the char out kernel routine we used last time. We have some data to place in memory, so our first instruction will be another jump start to hop over it. For our data, we have 2 operands, hex 1234 and 5678. When we define 16-bit data values like this, remember that CA65 will store them little endian, so the hex 34 will come before the hex 12 in memory. We are calling these variables foo and bar. Then we have a space reserved for our resulting sum, which will also be 16 bits. And we will similarly store it little endian to be consistent, but then print it big endian at the end of our program to be more user-friendly. With all our data defined, we can now have the start label and get into the actual code of our program. At the start of execution, we clear the carry bit and add foo and bar, starting with the low bytes as we saw earlier, storing the sum in result. Then we add the high bytes together, along with the carry bit, if set, and store that in result plus 1 to complete our 16-bit result. Then we call a heretofore unknown subroutine called print hex, but you can probably see where this is going. We retrieve that low byte of result back to A and then call print hex again. Obviously, we are printing a result as a hexadecimal text string to the display, and by starting with the high byte, it will be a big endian value. After the return instruction from the main program, we can lay down the print hex subroutine so that it's outside the path of the main program's execution. What we want to do here is print out the upper 4 bits first as a hex character, or nibble, and then the lower 4 bits for another hex character. So first we do a PHA to push the value of A to the stack to get it back later quickly. Then we shift A right by 4 bits, filling the upper 4 bits with zeros, and what used to be the upper nibble is now the lower nibble. This will give us a value from 0 to hex F, so we can then just print out that hex character with yet another subroutine called print hex digit, which will take that value in the accumulator. Then we pull that original value of A back from the stack so that we can now mask out that lower nibble with an AND that clears out the upper nibble, and then print out the hex character for what's left behind. Then we return back to where print hex was called. For print hex digit, we are again expecting our input value to be an A, so we need to determine whether the character we are printing is going to be a decimal number or a letter. So we immediately compare the accumulator with hex A, and if it is A or higher, it will branch to the @ letter label. That @ sign indicates that this is what is called a cheap local in CA65, which means that this label is only available in between the preceding and subsequent regular labels. This is an easy way to reuse label names in your code where you don't expect anything outside of a local scope to reference it. If the input value was actually less than A, then it can be printed as a numerical character, which means we just have to OR it with hex 30. Then we do an unconditional branch to @print. If we had branched to @letter earlier, then we need to add hex 37 to the accumulator to get the needed letter character in Petsky, where A is at hex 41, at least as far as the care_out function is concerned. Petsky is weird, especially compared to ASCII or Unicode, and we'll get into that in a later episode. In both cases, we fall to the @print label, where we call care_out with the desired character in A, and then we return back to print hex or wherever this subroutine was called. And that's it for the code. Like before, we have a simple build script that will assemble this code file called math.asm and generate an executable called math.prg. So let's build it now. Okay, so let's run the build script. Now we can see that math.prg has been built, so let's copy it to an SD card and run it on the X16. Let's do a load math.prg and then a run. And there we go. Our program has printed out 68AC, which is indeed the hex sum of 1, 2, 3, 4, and 5, 6, 7, 8. Well, that was exciting. You could go back and modify the file and reassemble it to try adding different numbers, or hack about in RAM and change those foo and bar values in memory, as indicated in the machine code listing in math.list. In a later episode, we'll see how to take live input from the user, but for now, we are done with this lesson. So I hope you found this episode pretty easy to take in. It's definitely a bit shorter than the others, but we covered a lot of ground and really uncovered the reason for the 65CO2 to exist in the first place, to do some math. It wasn't too hard, right? I wouldn't want you to look bad in front of Barbie, but you can go ahead and put any questions you have in the comments, and I promise to read only the most embarrassing ones to her. But seriously, please like and comment and let me know how you're doing and what you think may need some more clarification. We can always do a review lesson at some point to address some of those issues. The better the engagement, the better I can make these videos, so bring it on. If you want to know when the next lesson comes out, make sure you subscribe to my channel and click the bell to receive notifications. If you can't wait that long, click the join button or become part of our Patreon community and get early access to my videos ad-free like the folks you see here. So until the next episode, I hope to see you here again soon. Bye-bye.